All right, welcome everyone. Look, as an environmental engineer, you're constantly making judgment calls, right? But what if you could back those calls up with hard numbers? So today, we're going to break down the core statistical tools you need to do just that, pulling straight from Chapter 9 of Walpole's Statistics for Engineers to help turn all that uncertainty into confident, solid decisions.
So let's kick things off with a classic engineering problem. There's this new alloy for your water treatment pipes. It's supposedly stronger, but of course, it's more expensive. Your boss comes to you and asks, is it worth it? Yeah, a gut feeling just isn't going to cut it here. You need data. This is exactly where statistical estimation becomes your best friend. Let's see how it works.
Okay, so to answer that question, like a pro, we have to be super clear on one thing: the huge difference between just guessing and doing a proper statistical estimate. They sound pretty similar, but you know what? In our field, that difference is everything.
Okay, so we always start with what's called a point estimate. It's basically your best single shot, your best guess. So if you test a few of those new pipes and you calculate the average strength, that's your point estimate. It's the most logical starting point we have for understanding the strength of all the pipes, based on the little bit of data we actually collected.
But here's the thing, right? We know our small sample of pipes probably isn't a perfect picture of all the pipes out there. There's always going to be some uncertainty. And that's where an interval estimate is so useful. Instead of just one number, we create a whole range of believable values, and we call that a confidence interval. It's like we're building a safety net around our best guess to account for the fact that samples can be a little random.
And what's so cool about this, and really powerful, is that pretty much every confidence interval you'll ever build follows the same basic formula. You take your point estimate, your best guess, and then you just add and subtract a margin of error. And that margin is built from two things: a critical value, which comes from how confident you want to be, and the standard error, which is just a measure of how wobbly or variable your sample is. We'll dig into those in just a minute.
Okay, so before we can even think about comparing two different alloys, we've got to get really good at analyzing just one. Let's make sure we have the basics down solid by focusing on a single sample problem first.
So let's walk through a classic example together, the kind of thing you'd see in your textbook. An environmental engineer wants to get a handle on traffic flow. Before they can even suggest a change to an intersection, they've got to know what's happening right now. They need a baseline for the average stop time. So they head out to collect some data.
Okay, so the engineer heads out, watches 25 cars, and times them. They find the sample average, what we call x bar, is 13.2 seconds, and the sample variance, which we call s squared, is 4. That's it. These three numbers are everything we need to start building our confidence interval.
This visual here really gets to the heart of where our confidence comes from. Just imagine our engineer didn't just take one sample of 25 cars, but did it hundreds of times. As you can see, each sample would give them a slightly different average. And if you were to plot all those different averages, you'd get this really nice, predictable bell curve you see on the right. We call that the sampling distribution. The big idea is that we can use the rules of this theoretical distribution to say something really powerful about our one single sample.
Okay, now we've hit a really crucial fork in the road in our analysis. This is a question every single one of you will face when you do this, and getting it right is absolutely key to building a correct confidence interval.
So remember that formula we saw a minute ago? One of the key ingredients was the critical value. To find that number, we have to pick the right tool for the job. Do we use the z-distribution? You probably know it as the standard normal curve. Or do we use something else called the t-distribution? So how do we choose?
You know, it actually boils down to one simple question. Do you know the true variance of the entire population? If you did, and let me tell you, that almost never happens in the real world, you'd use the z-distribution. But for like 99.9% of the problems you'll actually face, you don't know it. All you have is the variance from your little sample. And because of that extra bit of uncertainty, we use the t-distribution. It's just a bit more cautious, giving us a slightly wider and frankly more honest interval.
So for our traffic data, it's the t-distribution all the way. We just follow these 4 simple steps. First, we find our degrees of freedom. Then, we go look up the t-value that matches. After that, we calculate the standard error. And finally, we just plug everything into our formula. The result tells us that we can be 95% confident that the true average stop time for all cars is somewhere between about 12.4 and 14.0 seconds. Boom!
All right, see? Now that we've got that single sample stuff down, we can take that same logic and apply it to our original problem, comparing those two different alloys.
So we're back to our two alloys, A and B. We don't really care about the exact strength of each one by itself. What we really want to know is the difference between them. Is one of them actually stronger in a way that matters? That's the goal.
All right, so we run some tests on 6 little pieces of each alloy, and you can see the data here. The average strengths are pretty close. So the big question here is that tiny difference we're seeing in the averages a real thing, or is it just random noise from the samples we happen to grab?
You'll see the process is actually super similar to what we just did. Our best guess, our point estimate, is just the difference between the two sample averages. To get a better handle on the wobbliness of our data, we pool the variance from both samples together. It just gives us a stronger estimate. But here's the most important part. When you get your final interval, you have to look for one thing. Does it contain the number 0? If 0 is in that range, it means it's plausible there's no difference at all between the alloys.
Okay, this is all great, but I bet you're asking a super practical question right now. How in the world did we know to test 6 pieces of pipe or 25 cars? Why not 100? How many samples do we actually need to take?
Well, the good news is we don't have to just guess. We can actually calculate the sample size we're going to need before we even start the experiment. All we need to do is decide on 3 things up front. First, how confident do we want to be? Second, how much error are we okay with? And third, we need a rough idea of the standard deviation, which we might know from old data or a quick little pilot study.
So let's circle back to our traffic example for a sec. Let's say the engineer decided they wanted to be 95% confident and that their final estimate had to be accurate within just 1/10 of a second. Well, you just plug those numbers into the formula, and it would tell them they need to clock at least 154 cars to get the job done right.
Okay, so let's zoom out for a minute and talk about the big picture. Why does this all matter? How is this going to be part of your actual day-to-day job as an engineer?
The main thing I want you to take away today is that this stuff, statistical estimation, it's not just some chapter in your textbook you have to get through. It's a real professional tool. It's what lets you go from saying, I think this alloy is stronger, to saying, I am 95% confident that the difference in strength is between this value and that value. It's how you make decisions you can actually stand behind with numbers.
And this quote from Walpole really hits the nail on the head. It reminds us that our single best guess is almost always going to be a little bit wrong. We're always working with just a piece of the puzzle. Our job as engineers isn't about being perfect. It's about being honest about the uncertainty and being able to measure it and explain it to people.
And all of this leads us right into the next big question. Estimating a range is great, but what if your boss needs a firm yes or no answer? Is this new process better or not? Well, that's when we step out of estimation and into the amazing world of hypothesis testing. Thanks so much for watching.